Let's say 3 different operators measure the same part with a micrometer. One reads 20.00 mm, another reads 19.98, and the third reads 20.02. Same tool, same part, so why are the values different? Most of the time, the problem is not in the micrometer, but in how it is used and how the result is interpreted. In this video, we take a closer look at the micrometer. The micrometer is one of the most critical precision tools in machining and in measurement rooms. It converts small size differences, too small to see with the naked eye, into numbers. For external dimensions we use an outside micrometer, for internal diameters we use an inside micrometer, and for depths we use a depth micrometer. The types are different, but at the heart of all of them is the same idea, a very precisely manufactured screw, and a scale system that shows exactly how much that screw has turned. The idea of using a screw movement for measurement goes back to a 17th century astronomer. The English astronomer Gascoigne used a screw mechanism to set and measure the angle between stars. This is considered one of the first steps towards using screw motion for length measurement. Later, James Watt brought this idea into the workshop and built one of the first bench-type micrometer devices. We see the concept of the U-shaped frame for the first time in his setups. In the 19th century, Palmer designed the handheld, U-frame micrometer that we recognize today. Then Brown and Sharpe took this design and turned it into a pocket-sized micrometer. That became widely used in machine shops. In this way, the micrometer became a standard tool of the machine workshop. So behind this small tool we hold in our hand there is astronomy, steam engines, machine tools, and hundreds of years of engineering knowledge. Now let's take a closer look at a classic outside micrometer. The U-shaped main part is the frame. On one side we have a fixed measuring surface. We call this the anvil face. On the other side there is a movable spindle that travels back and forth. The fixed scale with lines on the body is the sleeve scale. The cylindrical part that rotates on the outside is the thimble. Near the tip, the part that makes the clicking sound is the ratchet stop. Its job is to keep the contact force between the spindle and the part as repeatable as possible. When we take a measurement, we read the sleeve and the thimble together to obtain the actual value. Now imagine a metric micrometer that measures from 0 to 25 mm. In this case, the screw advances, for example, 0.5 mm per full turn. If there are 50 divisions on the thimble, dividing 0.5 mm by 50 gives us steps of 0.01 mm. Let's go through a reading example. On the sleeve scale we can see all the marks up to the 7 mm line, so that is 7.00 mm. After that we see one extra half millimeter mark, which adds 0.50 mm. Now we are at 7.50 mm. If the 12th division on the thimble lines up with the index line on the sleeve, that adds 0.12 mm. In total, we read 7.50 plus 0.12 is equal to 7.62 mm. In theory everything is clear, but the biggest factor that spoils the measurement is how hard we tighten the micrometer. A micrometer is not a vise. If we tighten it too much, especially on thin parts, we elastically compress the material, and the reading becomes smaller than the true size. That's why using the ratchet stop at the moment of contact is so important. As we approach the part, we switch to the ratchet, and once we hear 3 or 4 clicks, we stop. Common mistakes include measuring without removing burrs and dirt from the part, using the micrometer without cleaning the anvil and spindle faces, placing the part at an angle in the micrometer, and keeping the tool and the part in warm hands for a long time. All of these can shift the measurement by microns, especially when tolerances are tight. Regular checking is essential for precision measuring tools. For micrometers that measure from 0 to 1 inch or from 0 to 25 mm. When the anvil and spindle are brought together gently, the zero lines should align exactly. For micrometers with a larger measuring range, we use block gauges or ring gauges of appropriate size to check them. On the maintenance side, the rules are simple. Wipe the measuring faces with a soft cloth after use. Apply a very light protective oil film if needed. Store the micrometer in its own case or in a protected drawer. And avoid leaving the anvil and spindle fully clamped together. Keep a slight gap between them. We should remember this. If a micrometer is used correctly and stored correctly, it can remain reliable for many years. In summary, a micrometer is a precisely made screw and a scale system that magnifies and displays the movement of that screw. But behind it, there is a development process that spans centuries and a very deep body of metrology knowledge. In the next video, we'll continue exploring other pieces of measurement equipment. If you'd like to follow the measurement equipment series, don't forget to subscribe to the channel.